You can all see this, right? I have a lot of material to go through, so I decided I would present it in this format. You're all digesting your lunch anyway, so it doesn't matter. Okay, so here is the crazy plan. I spent a lot of time on my first lecture, taking 2.5 hours to do that. I have 2 more lectures and an hour to do that. So the idea is I'm going to go super, super quickly. But I could also skip some stuff. But of course, I will make all my slides available at the end, so don't worry about it. And some of the stuff I've talked about before, so you could go to MLSS 2015 and you could get a slightly outdated version of the same talk on video lectures. Okay, so so like I said before, I've done things in reverse, and now what I'm going to do is actually go through some of the background material, some of the foundations. Okay? So in the spirit of doing things super quickly, let me get this ready. Okay, so here's what would have been lecture 1, okay, the background material. So you've already seen this. We're going to view machine learning from the point of view of probabilistic modeling. And, you know, the workhorse of that is this Bayes rule. And the plan for this lecture is I'm going to try to talk about a little bit about the foundations of Bayesian methods, about intractability, a very brief kind of whirlwind tour of approximation tools, and some advanced topics and some discussion. I'll try to go through that maybe in half an hour or something like that. It's shortened from a 3-hour tutorial I gave at ICML like 10 years ago. But, you know, I think I can cover the highlights in half an hour, and you'll get a good sense. Then in the next half hour, I'm going to try, if I get to it, I'm going to try to talk about graphical models. And some advanced topics in graphical models, like kind of the modern view of how we can combine graphical models with deep learning. And I know Max has talked about some similar things, but repetition doesn't hurt. That's what Max told me. I asked him for copies of his slides. Is he here now? No, now he's gone. Now I can talk about it. I asked him for copies of his slides, and he promised them to me, but he didn't send them to me. But it's okay. And then he said, "Oh, repetition is good." That's not good. What's happening now? That's Max sabotaging me from the airport. Okay, good. So this is the outline. This is the more detailed outline, and the warning, some parts will be skipped. So machine learning is all about kind of solving certain canonical problems like classification. All problems have the same source of ingredients. You know, there's data. Well, the thing that drives all machine learning is data. And there's something that you could call a model, and the model generally has some parameters, and there's usually some goal that you have in solving that task. Okay? So here is like linear classification in that framework. I don't need to go through this. It's very basic for people here. Here is like polynomial regression in that framework. Your data are x's and y's, and your model might be a polynomial function with some noise. The parameters are the coefficients and the noise standard deviation, and your goal is to infer the parameters from the data and predict future outputs. Here is clustering or density estimation in the same framework. Your data are these little blue dots. Your model is maybe a mixture of Gaussians or something like that. That model has some parameters. Your goal is to infer the parameters of the model from data. You might use it for density estimation, or you might use it to infer whether several points belong to the same cluster or not. So all of these kind of machine learning problems, not including decision problems like reinforcement learning and things like that, the basic sort of data modeling machine learning problems have this same format. And as I've said before, we can use you know, this probabilistic framework for handling all of these problems in a very unified way. So here's how you would fit a Gaussian if you were a Bayesian. Okay, the difference is, this is a very, very simple example. I have a bunch of data points, and my model in this case would be, say, a multivariate Gaussian, and the parameters of the model are the mean vector and the covariance matrix of the Gaussian. And rather than fitting that Gaussian by finding a single mean and covariance matrix to fit the data, what I would do is, in that Bayesian context, I would have a prior distribution over where the mean and the over the mean and covariance matrix. Then I would condition on the data, and what I would get is a posterior distribution of the mean and covariance matrix that captures the fact that given a limited amount of data, I might be actually uncertain about what the mean is and uncertain about what the covariance matrix is. So one way to visualize it is you could show a kind of Gaussian ellipse wiggling about to show that the fact that it's uncertain. The more data you have, clearly it will become more and more certain until it converges to the maximum likelihood. Okay, so that's it. That's sort of Bayesian machine learning. That's all you need to know. Go home. Okay. Okay. No. Okay, so I'm lying to you. I mean, that's it, but in practice, there's a lot more. So here are some questions we're going to answer. So what motivates this framework? You know, like why should we care? I talked a little bit about that, but I'll talk a little bit more formally about that. You know, this question that troubles a lot of people, where does the prior come from, and how do we do the integrals that we need for Bayesian inference? So these are the three questions I'm going to try to answer. And I'll start by what motivates the Bayesian framework, and I'll give a couple of different answers to that. So one of them is going to come from not thinking about statistics, but thinking about AI. And this actually, you know, goes back a few decades to the, I think, 1940s. And the question is, imagine I was trying to build a system that reasoned about the world, that had beliefs about things in the world, okay? So imagine it's a robot. In order to behave intelligently, the robot should be able to represent its beliefs about propositions in the world. You know, is there a wall here? You know, can it go this way? Is the battery low? Whatever it is. Now, what we want to do is we want to represent the strengths of these beliefs numerically in the brain of the robot, okay? And now what we want to know is what mathematics should we use to manipulate strength of belief, okay? So, as I said, these sort of ideas go back to Cox in 1946. They were elaborated by James in 96, and then there's a nice review paper from 2003 on this. The concept here is going to be we're representing strength of belief. Let's call it B of X to represent the strength of belief in or plausibility of some proposition X. And we're going to make some assumptions. We're going to say, we're going to represent the strength of belief by some real number between 0 and 1, where 0 means that the system is going to believe that X is definitely not true. X means that, 1 means that X is definitely true. So the two extremes are logic, right? And in between, we have strength of belief, and then we're going to have an expression B of X given Y, which is going to represent the strength of belief that that X is true, given that we know that Y is true. Okay. So then, what the Cox Axioms correspond to is some rules by which these strengths of beliefs might have to operate. So, strength of belief or degree of plausibility should be represented by real numbers. There should be some qualitative correspondence with common sense about how the strength of belief might increase or decrease given evidence. And then there should be some consistency. For example, if a conclusion could be reasoned in several ways, then each way should lead to the same answer. So for example, if you're conditioning X on Y and Z, then the order in which you condition your belief on X, given that you know that Y and Z are true, should not depend on the order in which you manipulate, in which you condition on Y and Z being true. Another thing is that the robot must always take into account all relevant evidence. So you can't just say, I have a belief about X given that I know Y and Z are true, but I'm going to arbitrarily choose to flip a coin, and if it comes out heads, I'm going to ignore that I know that Z is true. Okay, that's sort of not allowed. You're not allowed to ignore things that you know. And equivalent states of knowledge are represented by equivalent plausibility assignments. So this is just another technical thing. Okay? If you believe in these axioms, then the consequence of this is quite interesting. The consequence is that these belief functions must satisfy the rules of probability theory, including the sum rule, the product rule, Bayes rule. And so this basically motivates why probabilities can be used not just for frequencies of repeatable experiments, which is what frequentists do, but for representing strength of beliefs in artificial systems, or maybe humans and animals as well. Okay? Rational artificial systems. That excludes humans and animals. Okay, so here is another motivation. This is a motivation for probability theory and Bayesian inference that comes from decision-making or gambling. It's called the Dutch book theorem. And the idea is, imagine you have some strengths of beliefs, like, your belief about, like, what the scores are going to be in different World Cup games or something like that. And so now imagine that you're willing to accept bets with odds proportional or better than the strengths of your beliefs. Okay, so one way in which people try to assess strength of belief in people is they will say, would you be willing to take this bet or not? Okay, so that implies that if your strength of belief in something like X is 0.9, that implies that you'll accept a bet where if X comes out true, you win $2, let's say. If X comes out false, you lose $9. Okay, so that's what it means to accept bets proportional to or better than the strength of your beliefs. Now, if that's the case, then unless your beliefs satisfy the rules of probability theory, including Bayes' rule, then there might exist, or there will exist, a set of simultaneous bets called the Dutch book, all of which you're willing to accept, for which you are guaranteed to lose money no matter what the outcome. Okay? So this isn't about whether your beliefs are correct or not. This is really about whether your beliefs are consistent with each other. That your belief system is not self-inconsistent, right? And so the only way to guard against such Dutch books is to ensure that your beliefs are coherent. In other words, they satisfy the rules of probability theory. So another reason why we can use probability theory to represent strength of beliefs. Okay, so those are sort of two philosophical arguments for sort of probabilities in AI and decision-making systems. But now let's relate it to some familiar concepts. Again, fairly basic but important stuff. So one of the concepts is asymptotic certainty. So that just says, assume you have some data, dn, consisting of n data points, and it was generated from some model with some true parameters theta star. This is kind of like how statisticians might think about things. Then under some regularity conditions, which I won't go into, this sort of involves kind of that the model is identifiable and stuff like that. As long as you put, again, I'm being a little bit loose with my mathematical language. As long as you put non-zero probability mass around theta star under your prior, which in common language means as long as you didn't say that theta star was impossible beforehand, because if you said theta star was impossible beforehand, no matter how much data you see, you'll still believe theta star was impossible. Okay? So you have to give some prior mass to theta star and the region around it. Then in the limit of infinitely much data, your beliefs will converge to a delta function on theta star. So you will converge to the truth theta star. Okay? So that gives you some confidence that things will be all right. There are a bunch of regularity conditions and so on. Now, in the unrealizable case, this is the case where the data was generated by some distribution p star of x, which is not modeled by any theta among the sort of parameters that you're considering. Then your posterior distribution in that limit of infinitely much data converges to a delta function around theta hat, where theta hat minimizes the KL divergence between the truth, p star of x, and p of x given theta. Okay, So what does that mean? Geometrically, what that means is you'll converge to the parameter values that are closest in KL distance from that truth. And actually, if you spell out what that means, the closest in KL distance from the truth is actually equivalent to the maximum likelihood parameters. Okay? So Bayesians, you probably all know this, but the Bayesian setting under some regularity conditions converges to maximum likelihood if you have enough data. Okay. Now remember, the regularity conditions generally involve the parameters, for example, not being, they're not being symmetries in the parameter space, which doesn't hold for example, a neural network. And they also only hold, these results mainly hold for finite dimensional parameter spaces. So in the setting of Bayesian nonparametrics, this stuff is much more subtle. Now there is another interesting concept called asymptotic consensus, which talks about what happens to two different Bayesians if they're presented with the same data. And what you would hope is that they should converge to the same beliefs. And this is basically what this result says. Consider two Bayesians with different priors. They start out, one with prior P1 of theta, another one with prior P2 of theta, who observe the same data. Now, here's the important thing. Assume both Bayesians agree on the set of possible and impossible values for theta. So again, we can't say, if one Bayesian says, these values of theta are the only possible ones, but everything else is impossible, and another Bayesian says, no, these values of theta, the Republican values of theta are the only possible ones, and the Democrat ones are impossible, then no matter how much data you show them, they will not converge to the same beliefs. But if these sets coincide, then in the limit of infinitely much data, the posterior beliefs of these two systems will converge to each other. Of course, they both converge to some maximum likelihood or something setting, but they'll converge much quicker than that to each other. So that's what consensus means. Okay, so I'll maybe skip over this. This is like, a little exercise in thinking about like Bayesian inference with a coin toss. I'll share the slides. You can do it in your own time. It's very, very easy stuff, but it's useful. Okay. So now let's talk about this problem of model selection, which is something I've alluded to in the context of the automatic statistician, that we're trying to do this model selection thing. So here, this is a really fundamental problem in machine learning. It was, maybe more important in people's minds when we were trying to do a lot of learning on fairly small data sets. There are still, as I said, lots of small data problems out there in the world. If your problem is you have way too much data and you can't compute with it, then some of this stuff is less relevant. But think about the problem of model selection. That's the problem of, imagine in this case, let's say in this simple example, we're looking at fitting polynomials to data. I have a bunch of data points, these red dots, and I'm trying to fit a function y as a function of x, and I'm going to consider constant, linear, quadratic, cubic, quartic, quintic, etc., 6th and 7th order polynomials. So what you can see here, this is just a canonical example of where you might have, at the one extreme, some underfitting. So there might be structure in the data that your model has not captured. That's what underfitting is. And at the other extreme, there might be overfitting, in which, in this case, we can fit the training data perfectly, but you're making wildly crazy predictions at other points. Okay? So we want machine learning and statistics principles that can avoid both underfitting and overfitting. And of course, that's just a canonical example of something that occurs in lots of other places in machine learning, like how many clusters do you have in your data? What's the intrinsic dimensionality? For feature selection, is this input relevant to that output? For fitting HMMs or dynamical systems, how many hidden states should you have? If you were doing neural nets, what architecture should you use? How many hidden units should you have? If you're fitting graphical models, like, what should be the structure of the graphical model? All these are examples of the same kind of problem. They occur everywhere in machine learning and statistics. So here is the sort of key concept that I was alluding to before, which is this concept of Bayesian Occam's razor and model selection. So the idea is the following. We can solve all of those problems in principle just by using the sum rule and the product rule. We don't need to allude to any further principles or regularization or any other things. In fact, we can think of regularization and principles like that as approximations to trying to do this thing. So let me describe what that is. So here's the idea. I want to compare model classes M and M prime, two different descriptions of my data, given the data. And of course, what I can do is I can compute the posterior probability over the different model classes, 4 or 5 Gaussians in my mixture model, or 3 or 4 hidden units in this layer, or whatever it is, by computing Bayes' rule. And there's a term in here, P of M, which is a prior that you're putting in that might explicitly say that I prefer simpler models to more complicated models. Like it might say, I just like third-order polynomials better than 17th-order polynomials, or I believe that that's a more sensible representation of the data. That's what that prior might say. The interesting thing is that that's not really the workhorse that's going to get you automatic penalization of models for being too complicated. This term in red, the marginal likelihood, is the one that's actually going to be the driving force for penalizing models for being overly complicated. Let me explain how that works. So by the sum and product rule, the marginal likelihood is the integral, that's the sum rule, of the likelihood times the prior integrated over the parameters. No new principles here, just sum and product rule. So what is that? That's sometimes also called the integrated likelihood. It's integrated with respect to the prior because that's the description of the full model. The model says that there's some parameters and there's some prior that captures the distribution over those parameters under the model. So the model, we all know that if I fit a 17th order polynomial to the data, I can fit the data better than if I fit a third order polynomial because it has more parameters. So it's certainly true that the likelihood, if I were to optimize the likelihood, more complicated models would give the data higher likelihood, right? But there is no optimization principle in Bayesian statistics. There's just the sum rule and the product rule. So how is that different? The marginal likelihood here is, it turns out, not going to necessarily be higher for the more complicated model. In fact, if a model is too complicated, the marginal likelihood will automatically penalize that model for being too complicated. Where does that come from? How does that work? So that's the mathematical expression for it. And here are 3 ways of interpreting that marginal likelihood in words that might give you some intuition about why this mathematical expression penalizes models for being too complicated. So the first way of expressing this is the probability that randomly selected parameters from the prior would have generated data D. What that means is if I have a simple data set and I try to fit it with a complicated model, the complicated model is very flexible. So randomly generated parameter values under the complicated model will be able to generate lots and lots of different kinds of data sets. So the probability that they assign to this particular data set might actually be quite low. One way to estimate that is just generate parameters at random and average the likelihoods together. And that could be a lot lower for the complicated model. Here is another way of just describing the same equation. It's the probability of the data under the model averaging over all possible parameter values. It's the same sort of statement. If you like information theory, then I can interpret log base 2 of 1 over this quantity in bits, and it's the number of bits of surprise at observing data D under model M, where entropy, it turns out, is the average surprise. That's the definition of information theory. So what does that mean? That means that you should maybe choose a model for which the data is least surprising. Okay, and so, you know, if I had a data set that looked like this, and I said, you know, what would surprise you more? If I told you that this data came from a linear model, or if I told you that this data was randomly generated from a 17th order polynomial, you would say you would be more surprised that this data was generated from a 17th order polynomial, because it would have to be a very lucky 17th order polynomial to line things up along a line. That's exactly what, that sort of, you know, human conceptual intuition is exactly what's encoded by the sum and product rule of probability theory. A sort of nice abstract representation of this is, imagine I lined up all data sets of some size n along this axis in some arbitrary order. And now I can consider different models. A simple model, like a linear polynomial, basically assigns a lot of probability mass to simple data sets that look like this, right? A more complicated model, like that 17th order polynomial, can model more different kinds of data sets. So it spreads this mass over more possibilities. But because of probability theory, because these models, P of D given M, has to normalize over data sets, that fact that we've chosen to define proper probabilistic models that normalize means that if I'm going to spread my bets over more data sets, then necessarily the mass that I have is 1. Necessarily, I can't model the simple data sets as well as the simple model. Okay? So the area under each of these curves is 1, no matter what you do. And so now, if I observe a particular data set, then I can reject models that are too simple, that they can't capture that particular data set, but I can also reject models that are too complicated, that maybe spread their mass over too many data sets, so they can't model that particular data set as well. And the hope is that you end up with the just right model. And that's exactly how the sort of demo of the sort of automatic statistician for time series and for Gaussian process classification, that's exactly how it figures out the model structure, the kernel to use. It's just using marginal likelihood. Okay, so here that concept is applied to polynomials, and what you can see is the same data as before. The blue curve is the maximum likelihood fit. The green curves are 20 samples from the posterior distribution of polynomials given some prior over the parameters, showing you the uncertainty. And then this bar chart here is the marginal likelihood or model evidence for different orders of polynomials. And what it's telling you is, given these 8 data points, constant is a possibility, linear, quadratic, and cubic are all possibilities. Quartic and higher have very low marginal likelihood. You can't see them. You could see them on a log plot, but you can't see them on this plot. They're just quite low. And the favorite, the marginal likelihood's favorite choice is quadratic, basically. So, you know, I could show you a demo of this working with random data sets. And as the obvious thing is, if you give it more data, then it becomes more peaky around the truth. And in this case, the data was generated from a quadratic. So we can discover that automatically. Now, for the polynomials example, we can do this thing exactly, can do these calculations exactly and analytically, but in other settings, is computationally intractable. So now I've been speaking quickly, now I'm going to accelerate, and I'm going to skip over some aspects of choosing priors, because I think there might be some interesting stuff I can talk about in terms of graphical models and neural networks, some more modern stuff. A lot of this stuff is textbook material. I'll just zip through it really quickly so you get a sense of what I'm talking about. So there are a lot of different schools of thought of where your priors should come from. People try to come up with objective priors. that captures some notion of uninformativeness. People try to come up with, some camp says, forget that, that's a bit hopeless. Your prior represents your beliefs, so just go with whatever your beliefs are based on any knowledge you have of the problem. They're subjective, but that doesn't make them arbitrary. You know, that just means that you should express your beliefs as best you can and then go from there. Not mutually exclusive, but people can define hierarchical priors, and there's like empirical Bayes where you learn, you maximize some of the parameters of your prior, like your hyperparameters from the data. And I have a few slides on, you know, like various versions of subjective and objective priors. You know, in case I haven't kind of put my cards on the table, I'm pretty much a subjective Bayesian. I think all modeling involves assumptions, and assumptions are, you know, the only thing in the world, you know, of modeling is data and assumptions. Data is the stuff that you're given. Everything else is assumptions. And the Bayesian framework, what it does, it forces you to express your assumptions as explicitly as possible as a distribution over possibilities. And then everything is automatic given those assumptions, modulo the fact that you have to do computations. Okay. So there's empirical Bayes, exponential families. Again, another exercise to think about. This is actually quite subtle. How would you choose priors for a logistic regression if you're going to do Bayesian logistic regression? It turns out it's not easy. And it's partly not easy because, you know, if you're going to do logistic regression, your prior over the parameters should really depend on your beliefs about what the x's are, right? Because in a neural net as well, the parameters, there's a dot product between the parameters and the x's. And so the scale of your prior about the parameters should depend on what you think the scale of your x's is. And that's why a lot of people in machine learning do things like they normalize their inputs before they stick it into their model. That's because if they didn't do that, their system would just not work on data sets that are scaled several orders of magnitude off from what they expected. So people do a lot of ad hoc stuff to compensate for the fact that you want to be robust to a lot of these assumptions about the structure of the data. Okay, there's a tutorial on how to choose stupid priors. And I think the key thing is, you know, the nice thing about Bayesian methods is that once you've actually fully formulated your model with priors and likelihoods and everything else, you can actually generate data. And then you can see whether that data matches your expectations. If the data looks really weird, then something's wrong about the way you formulated your model. Even before you observe your real data, your generated data should capture your knowledge. So, so in the next few minutes, so that was on choosing priors. I've sort of closed that off. In the next few minutes, what I want to do is give you a whirlwind tour of the computations involved in Bayesian inference. And again, there's an interesting kind of analogy here between what happens in most of machine learning, which is optimization, and what happens in Bayesian machine learning, which is integration. So let's look at that a little bit more carefully. The kinds of quantities that we're interested in Bayesian statistics and machine learning are generally averages or integrals, right? Because we want to average over the possibilities. When we compute the marginal likelihood, in this case, we're integrating over, you know, parameters. So that's an integral or average. This can be a very high-dimensional integral. And if we have latent variables, hidden variables in our model, then we're integrating both over parameters and hidden variables, and that could be even more complicated. The likelihood terms themselves could be complicated. All this stuff means there are some computational issues to worry about. Fortunately, there are, you know, many decades of work on how we can approximately solve integrals, just like there are many decades of work on how we can do optimization in high-dimensional space. So when I said many decades, I should have said a few centuries, because some of the ideas go back to people like Laplace. Okay, so we could start from here, and this is just a very quick list of a few commonly used methods for doing approximate integration. And we can mix and match these algorithms to a particular Bayesian method, and they all correspond to different points on a, let's call it a speed accuracy trade-off. So some of these things are super fast, like BIC, but they're not very accurate. Some of them are slower, like Laplace, and are a bit more accurate, and maybe variational methods and EP might be more accurate in some settings. MCMC is an anytime algorithm, so I can run it for as long as I want. The longer I run it, the more accurate results I'll get. Okay? Okay, so again, I don't want to spend too much time on this, but I'll spend a little bit of time on the first couple. Here's a sort of the Laplace approximation. What the Laplace approximation says is, what's our target? We want to compute this marginal likelihood. But as a side effect, we also want to approximate the posterior distribution over parameters. That distribution is what we're going to average with respect to when we make predictions. Okay? And what the Laplace approximation says, I'm going to skip over the equations a little bit. It says, here's how we're going to do it. We're going to optimize the parameters. So we call our favorite optimization routine. We find an optimum of the parameters, call it theta hat. At theta hat, I'm going to compute the log prior and the log likelihood. So I've computed those during optimization anyway. So that's a cheap thing to do, assuming you finish your optimization. And then I'm going to take my log prior and my log likelihood, and I'm going to penalize it by this term here. D over 2 log 2 pi minus 1/2 log of the determinant of a matrix. Okay? D is the number of parameters that I've optimized. And this matrix here that I'm going to take the determinant of is the matrix where the elements are the second derivatives of my log posterior, includes the log prior and the log likelihood, with respect to parameters theta I and theta j. So it's a matrix the size of my parameters squared. And what it corresponds to is the curvature of the posterior around the optimum. So the Hessian, the curvature of the posterior around the optimum. And of course, in very large models, in the models that Laplace used this on, they were quite small, so he could do that calculation by hand. In a neural network with 100 million parameters, that's 100 million by 100 million matrix, and you're not going to take the determinant of that. But you could try to approximate that. And in fact, if you look at the old neural network literature on optimum brain damage and crazy things like that, they were basically just applications of Laplace to neural networks. For model selection back in the 80s. Where does this expression come from? This is an approximation to the marginal likelihood, this golden kind of quantity that I said drives all of model selection in the Bayesian framework. And it comes from the fact that under regularity conditions, the posterior converges to a Gaussian if you have enough data. And so all you need to do is you need to compute the maximum of the posterior and the curvature, and you get a Gaussian approximation of the posterior around that point. And then the marginal likelihood is the integral, the volume of that Gaussian. Okay, that's your approximation for the marginal likelihood. And the volume of a Gaussian is related to the determinant of the covariance matrix of that Gaussian. So there's many ways of thinking about this. It's the sensitivity of your parameters in each of the different directions, the volume of the Gaussian. Whatever it is, it's a computational tool that involves optimization, computing second derivatives, and computing or approximating a determinant of that. And that's your penalty term for the complexity of the model. If you have a more complicated model with more parameters, this penalty term will be bigger. That's because it's approximating the marginal likelihood. Okay. Now, the Bayesian information criterion, or BIC, is basically taking the Laplace approximation and making it even more approximate but cheaper to compute. Remember, the determinant of this huge matrix might be too expensive. So, you might feel a bit lazy, or you might not have enough memory on your computer to do that. So what can you do if you're too lazy or don't have enough memory? Well, here's what you can do. You can take the Laplace approximation. You can say, let's ignore all the terms that don't grow with n, the number of data points. This thing here, has a log prior, which doesn't grow with n. So I'm going to just drop that. It has a log likelihood, which grows linearly with n. So I'm going to keep that one. This d over 2 log of 2 pi, that's a constant. It doesn't grow with n. I'm going to drop that. And the 1/2, the log of the determinant, well, the determinant of this matrix, each element of that matrix, those second derivatives, each element of them grow with n. It's quite easy to see that because it involves the log likelihood in there. So actually, the determinant of this matrix grows as n to the power of d, the dimensionality of the matrix, times some constant, which I'm going to drop. Log of n to the power of d gives me d log n. So here, instead of here, I get d over 2 log n. And this is an awesome equation. This is like super simple. All we have to do in practice is maximize the likelihood and penalize by the number of parameters over 2 times the log of the number of data points. Now, you could sort of use that, but if you wonder where it comes from approximating an integral. Okay? Super cheap to do. You can also rederive all of this if you like information theory, and it's called the minimum description length principle. But it's just the same thing. It's just a rephrasing of the same idea. Okay. So that was BIC. Then there is variational inference. And I think Max talked a little bit about variational inference, right? Raise your hand if yes, Max talked about variational inference. You believe that? You believe in that statement? Okay. All right. I'm going to skip over variational inference. Again, there's a lot of material out there that talks about it. There's sort of like the idea of variational Bayes, which is very similar to the EM algorithm. It's basically analogous to the expectation maximization algorithm, something I was kind of heavily involved in, but I'm going to skip over all this. There was another algorithm called expectation propagation. I'm going to skip over this as well because I only have 15 minutes. Again, another way of approximating integrals by basically passing messages in a graph. Kind of a neat idea that I'm trying to summarize in 2 slides, which I'm skipping. Then there is Monte Carlo methods. Again, many decades of people working on both Monte Carlo methods and Markov chain Monte Carlo methods for approximating integrals. And an MCMC method basically involves drawing samples. Let's say I'm trying to approximate this quantity, which is the posterior distribution over parameters, some unknown quantities given the data. And at a high level, the way I'm going to do that is I'm going to start with some thetas, and I'm going to apply a probabilistic transition to those thetas. So I'm going to perturb those thetas in some way, and that's the kind of called this Markov chain transition probability. So you go from theta to theta prime. And under certain conditions, I can define these transition probabilities very generally so that if I run these transitions long enough and I look at the thetas that I'm getting, then those thetas are actually drawn from the distribution I'm interested in. So I run this method for a long time, and then I take a subsample of the thetas I've observed, and that approximates over time the distribution, the posterior distribution of interest. And there are many, many easy ways of doing that. So like we can use this in probabilistic programs, for example, to sample over the space of hidden variables in a probabilistic. So again, I'm kind of skipping over this and skipping over this. Lots of good stuff to look at there. In fact, there was a machine learning summer school I ran in Cambridge in 2009, and there's still some lectures by Ian Murray which are widely viewed on video lectures on MCMC methods. So if you want to deep dive on MCMC methods, you could go back in history and look at the stuff from them. And not that much has changed because those methods have been around for many decades and they're really, really useful. Okay, so exact sampling, I'm going to skip. I'm going to do a few minutes of discussion. Nah. You can read the stuff in red. You know, this is just discussed by looking at the slides. Discuss with yourselves, right? Bayesian methods don't scale well, you know. It depends. I mean, in some cases, Bayesian methods can be thought of as just as, you know, optimization plus adding some noise. And so if optimization scales, then you can do approximate Bayesian inference, etc. Okay. Let me go on to the next stuff because I created some new slides. It'd be a shame not to use the new slides. Any questions while I switch gears? Questions? Questions? Yeah, questions. Okay, question. Okay, how can, as a subjective Bayesian, I believe in the prior and something incomprehensible like a neural net? That's a great question. The thing is that the parameters of a neural net don't mean anything. Okay, so I honestly don't have a prior on, you know, what the parameter in layer 7 of this fully connected layer should be, and that's ridiculous. That stuff doesn't mean anything. What the neural net does is it implements some mapping. Let's say it's a supervised network. It's a mapping from X to Y. So actually, the important exercise is to have reasonable priors on what the space of possible mappings from between observables is, and then come up with a prior on the parameters that is consistent with the prior over the relevant important stuff. So that's how I would handle that from a subjective point of view. Your beliefs are generally about things that make sense, that have to do with the real world, which is generally about data. Question, there was another question over there. Yeah.
Yeah, my question would be about the sampling methods. Today we have the problem that sampling doesn't work well in high dimensions. On the other hand, we try to use like variational approximations, but as it says, this is only an approximation. I mean, how could we improve this? How could we make like asymptotically exact posterior inference in this setup?
Yeah, that's a great question. So, so first of all, people who write papers on variational methods will start them with something like sampling doesn't work. Actually, sampling works incredibly well in a lot of settings. And it's just like, don't necessarily always believe the motivation for what the rest of the paper does. One of the nice things about sampling is that, in theory at least, a sampler's error is dimensionality independent. There's a constant that depends on the dimension, but as you run the sampler, the error rate of that sampler is independent of dimension. So physicists, for example, often use MCMC methods to deal with systems with hundreds of thousands of dimensions and so on. So it is true that it is hard to get samplers to work in some high dimensional cases. It's also hard to get them to work in some low dimensional cases. There's never a silver bullet for any of this stuff. The way I like to think about things is that on any particular problem, and a problem is a combination of a model and a data set, then there might be a class of inference algorithms that provides a good speed-accuracy trade-off. One of the nice things about sampling is that because they're anytime algorithms, I can run my sampler for a very short period of time, which could be quite cheap, and get a decent answer. And then if I run it longer, I'll just get better and better, in theory, at the cost of some memory. Whereas variational methods might converge very quickly, but then might asymptote because they've made independence assumptions that don't hold. So I do think there's just, I mean, I've worked on both, and so I don't have a favorite child when it comes to sampling or variational methods, right? I think the problem is it's hard to make these decisions. It would be better if we didn't have to think. And so part of the whole principle of automating machine learning that I talked about in the last lectures was, let's make life easy for people. Let's make them not have to think about the fact that actually the answer is quite subtle. Okay.
Yes, question.
Yeah, question.
Regarding the equation that you showed for the Bayesian information criterion, it was a very simple equation, and all the parameters are treated equally. It means that only the number of parameters matters. So, for example, when we have a mixture of Gaussian, we have different parameters like covariances and means, and also the responsibility of each component. So somehow counterintuitive that all the parameters are treated equally in that way.
You're absolutely right. And so this is where the speed accuracy trade-off comes in. In Laplace's approximation, you have this determinant of a covariance matrix. What that tells you is, it tells you that some parameters are very sensitive, the likelihood is very sensitive to some parameters, and those matter a lot. And some parameters are irrelevant, the likelihood is not sensitive at all to those parameters, those matter much less. So by throwing away that covariance matrix, we are treating all parameters equally, so it's a more crude approximation. Parameter counting is very dangerous. If you look at if I put that slide up more than a couple of seconds, you would have seen I had a bunch of caveats at the bottom, and one of them was parameter counting is dangerous because of exactly your question. Okay, so let me talk about, I have about 10 minutes or less. Continuing acceleration until we hit terminal velocity. Okay, so I have a whole nother lecture on graphical models, but that's okay. Again, you can look on previous MLSSs. I did talk about graphical models 2 years ago, I think, but I have some new material in here, so I want to just quickly get to that new material. Okay, so graphical models, they're about representing knowledge. And nodes correspond to random variables. Edges represent statistical dependencies between the variables. And they're a very nice framework because they abstract away the dependence relationships between variables, this idea of conditional independence, and also they're computationally useful because we can have efficient algorithms for computing probabilities that involve message passing on the graph. Just like, graphs are quite useful when you take derivatives in automatic differentiation, graphs are also quite useful if you're trying to compute probabilities because you can just do it by passing messages around. And so, here's just a definition of directed acyclic graphs, sometimes known as Bayesian networks, and what the independencies mean, and how to represent a little holistic model in a DAG. And then inference in a DAG, the message passing. I'm basically skipping over this, but showing you the slides anyway. So inference in a graph involves passing messages. There's nothing special. Again, I sound repetitive, but because it's true, all it is, message passing in graphical models, things like belief propagation, they're just applications of the sum rule and the product rule. Okay, they're just using the sum rule and the product rule on a graph where you can use the independence relationships to do that stuff efficiently. So, if you do it naively here, you might compute 20 terms. If you do it more efficiently, you might compute 8 terms. In general, you might get exponential gains by doing message passing on big graphs. Okay, and so I have a few slides where I talk about the general factor graph propagation. It's quite straightforward. In HMMs, this stuff was discovered many, many years ago under the term the forward-backward algorithm. Okay, the forward-backward algorithm is just message passing in HMMs, in hidden Markov models. It was also rediscovered in the signal processing community and the control community as Kalman filtering and Kalman smoothing. It's all exactly the same. In fact, it was quite revolutionary when a few machine learning people said, hey, this stuff, this was like in the, I was involved in this, so I remember very clearly, like this stuff in the early 90s, you know, people were like, this stuff you do in signal processing is exactly the same as this stuff that people in speech recognition do, and it's exactly the same as this stuff that these other people do, and it can all be written down in these two equations, and here's a generalization that holds for all trees and, you know, other graphs. And people were like, you're kidding, you know, this is, we have whole textbooks on this, and we didn't know that. And that was literally the response that people gave. Now, of course, we've moved on. And so, in fact, there is software for doing inference in graphical models, but they're all kind of subsumed by probabilistic programming in principle, because probabilistic programming can do things that are hard to express in graphical models. Okay. Let's skip over learning parameters, some of the new stuff. Okay. Yeah, that's what I said. Graphical models and probabilistic programs. Graphical models express conditional independence relationships between usually a fixed finite number of variables, whereas probabilistic programs define the relationships between variables through a computer program, a simulator that can generate the variables. And so probabilistic programs are generally more expressive than directed graphical models because they can capture things like the independence relationships or even existence of variables conditional on the values of other variables. That's very hard to capture in a graph because you have to write a node for every variable. But what about if this variable only exists if this binary variable is 1, and it doesn't exist if the binary variable is 0? You can't draw that in a graphical model. They can also express models, probabilistic programs can also express models with potentially unbounded number of variables, and they make explicit the functional forms. So that's just kind of where we're at with graphical models. Here's a couple slides on graphical models and deep learning. So conceptually, graphical models represent relationships between random variables. Deep learning or neural networks represent nonlinear functions. Okay? And we can mix and match these in many different ways. So for example, we can introduce hidden variables into a neural network, right? Like, for example, VAEs, variational autoencoders, are an example of hidden variables inside a neural network. Or we can use neural networks to model the conditional probability distributions in a graphical model. So I have a graphical model that goes from X to Y to Z, and in between each pair, I'm going to use a neural network to represent the relationship between Y and X. There's no problem with doing that. Okay? Now, historically, there's some really nice paper which is called, this paper called Connectionist Learning of Belief Networks. And it was really, again, Radford Neal in 1991. And it was a paper that tied backpropagation networks with graphical models. We made an explicit link between feed-forward neural networks with sigmoid units. And it said, basically, if we think of these units not as deterministic functions, but as binary random variables, each sigmoid is like a binary random variable, then we can represent the whole model as a graphical model with layers of units, a hierarchical generative model. We used to call them hierarchical back then rather than deep. Okay? And then if you want to do maximum likelihood in these models, you could do Gibbs sampling and sample over the hidden variables. So a really nice paper on that. You know, kind of inspired by that, a few years ago with Ryan Adams and Hannah Wallach, we tried to marry deep learning with probabilistic models, deep learning with Bayesian nonparametrics, which I haven't talked about, which is how would you get a probabilistic model that could learn the number of hidden units, the number of layers, and the types of units automatically from data in a kind of neural networky architecture. So, and we did this all with MCMC, and you know, I was very proud of this work, but you know, it wasn't very practical. It was just conceptually kind of interesting that you could marry, you know, automatic Bayesian model selection with kind of deep architectures. In fact, the networks were infinitely wide and infinitely deep. So, you know, how much better could you have than that? of course, I mean, it kind of worked. We would run it on MNIST, and it would say that it wants to use 3 layers, and it wants to have this many hidden units, and so on. So it sort of worked, but you know, it's never going to give you state-of-the-art stuff because MCMC is quite expensive. Maybe now we have more powerful computers, so we should just run this stuff again. So autoencoders. Autoencoders are an idea that, again, I'm gonna wrap up in the next 2 or 3 minutes, so don't worry. Autoencoders are an idea that have been around for a really long time. I used to actually teach it, and then I dropped it from my lectures because I thought nobody was interested anymore. That was in like the late 90s. So the idea is you have inputs and you map them to some hidden units, and then the hidden units map to some outputs, and you can think of this part of the network as an encoder or recognition network, and that part as the decoder or generation part, and you're trying to make the inputs equal to the outputs equal to the inputs. Okay? Classic autoencoder. Now, who knows, like, what does a linear autoencoder do? Who knows? Raise your hand if you know what a linear autoencoder does. Yeah. A linear autoencoder implements principal components analysis. So that was figured out in 1989 or so. There was like a classic paper on that. So autoencoders, the way to think about them is they're nonlinear PCA models. Okay. In fact, PCA is itself a special case of something which I consider to be sort of the mother of all latent variable models, which is called factor analysis. So factor analysis says I have some observed data, and my data is going to be modeled by assuming there were some k factors, and those k factors were independent, and they model the relationships in my observed data. Now, factor analysis is a mother of these things because it makes the most simplifying assumptions. It says the latent variables are all Gaussian, and the relationship is linear. So it's a linear Gaussian model. PCA is kind of a special case of factor analysis where you assume the noise variance on all of these is the same. And actually, if you look at a lot of the modern marriage between probabilistic models and neural networks, you can kind of trace it to a setting like this. So the mother of all latent factor or latent variable models is factor analysis, and PCA is its sister model, special case of it. That goes back to 1901 and 1904. Okay. Now we can do a few operations on that. My color scheme is the same, but the operations are different. Okay, so one operation is we can make things nonlinear or non-Gaussian. Okay, these models are linear and Gaussian in their assumptions, and nonlinear and non-Gaussian gives you various models like independent components analysis, which used to be the big thing in the late 80s, early 90s, or mid-90s actually, is a kind of non-Gaussian version of factor analysis. Really a cool algorithm still. Or that's the orange arrows. The blue arrows are deep or hierarchical versions of these things. And the problem is if you have a linear model, making it deeper is just a bit boring. It's still a linear model. So that's why I put an X here. That's sort of uninteresting corner of the cube. And the purple arrow is some of these models that were represented as these directed models have analogs that are undirected graphical models, where you're not generating y given x, but you're sort of jointly modeling x and y. And there is a model called products of Gaussians. Again, Max Welling was involved in that, and Chris Williams and so on. These are undirected models. Now, if you look at something like a restricted Boltzmann machine, that's a particular kind of, loosely speaking, that's an undirected model that looks a lot like factor analysis, but the variables are non-Gaussian, but it's still one layer. If you look in this box, you find a huge number of different kinds of models. We have hierarchical nonlinear factor analysis, or you could call it deep factor analysis, or deep Gaussian processes, sigmoid belief networks, which were what Radford Neal did in the early 90s, variational autoencoders, all this stuff I think of as, okay, here it is. So variational autoencoders I think of as nonlinear factor analysis. You have factors and you have a nonlinearity mapping to the data. And where you train it using a recognition model going in the opposite direction, kind of like that's your recognition model here. And you use variational inference to train that recognition model, but you can't compute the variational approximations exactly, so you do sampling. Okay, so that's where this kind of falls in, and you have other models like deep pulsar machines. Okay. Should I stop on this slide? Okay, here's a note on Ganz, because Ganz are very popular, and again, Ganz can be thought of in a very simple way. So, generative adversarial network. Who knows what GANs are? Raise your hand. Okay, a lot more people than other things. Okay, so assume you have a generative model that maps from a latent variable xn to some observed variables yn through a nonlinear function. Okay, that's what it is. And it happens to be implemented with a neural network with some parameters theta. The problem is, if I want to do maximum likelihood on that model, I have a problem. The probability of the likelihood, which is the probability of the training data given the parameters, well, I'm assuming it's IID over the data point, so it's the probability of each data point given the parameters. But the problem is computing the probability of the observed data given the parameters involves integrating over this vector of hidden variables, right? And that's intractable because the thing is nonlinear, unlike factor analysis where I can do the integral exactly. So that integral is intractable per data point. And now I just showed you that there is like, 50 years of different literature on how to approximate integrals. So we could use any approximation we want, variational inference, MCMC, expectation propagation, a recognition model, etc. But here's what we're going to do, which is different in Ganz. What we're going to do is, since we can sample data from this model, even though we can't compute the likelihood, what we're going to do is we're going to sample some data, and we're going to use what's called a two-sample test to train the model. And a two-sample test is a test to see if the data sampled from the model and the training data are drawn from the same distribution. Okay? Our generative model is good if the two-sample test can't tell apart between the training data and the sampled data. And our model is bad if it can't tell apart. So again, is basically nonlinear factor analysis trained using a two-sample test as a surrogate loss function instead of the likelihood, where that test is implemented using a discriminative model. But of course, there is again like 100-year literature on two-sample testing. So they're not better, but there are other ways of doing two-sample testing. Like, for example, you might hear about a maximum mean discrepancy as a way of doing two-sample testing. And you can take derivatives of that instead of a neural network. It doesn't work quite as well as having a discriminative model, but it's certainly useful to think about, combinations of things. Okay, I've gone way over, and I'm cutting into coffee break. So I'm going to basically stop there. Okay. Who's the boss? Can I take some questions, or everybody's dying for coffee?
I think we have time for some questions.
Okay, let's take a couple questions. My friend?
Yeah, works. So I have the impression that the view on Bayesianism in machine learning has moved away somewhat from the early Bayesian theorists and also current view in philosophy. So, for example, yesterday you classified Bayesianism as algorithms, which is, where others might view Bayesianism more as a fundamental understanding of the concept of probability or as a framework for indicative inference. So today you also talked about model checking and model criticism, which is rather not inductive anymore, rather deductive, so attempt of classification. I think Bayesians might say it's incoherent or irrational. yeah, what are your views on this?
Yeah,
this?
yeah.
Do you think it's problematic at all?
No, no. I think it's a great question. So it depends on the audience that I talk to.
I'm an outlier, I think.
No, but it's a great question. It's always good to have an audience with people with the right sampling of backgrounds to keep me honest. A lot of there is a difference between being a purely subjective Bayesian, a sort of a very clean, pure, coherent subjective Bayesian, which is certainly I kind of know how to be that if I want. The problem is that for me, actually being rational and being practical sometimes trumps being Bayesian. And so some of the things you need to do if you're going to be completely a pure Bayesian involve computations that are just intractable, and they also involve, really having confidence that you're going to believe your prior going into a problem. And so because of those two reasons, the intractability of the computations and the fact that you do want to be robust to your prior assumptions, it's useful to do things like some level of maybe model checking, even if you're uncomfortable with it, which I am. I mean, you can be kind of Bayesian about your model checking as well, but that's more complicated. And you can then think of approximate inference. The problem with the pure Bayesian view is that you only have finite computational resources, and so you're always sort of truncating your inference towards your posterior, and so you need to have some sort of measure of confidence in what that means. Sort of holding out some validation data seems a perfectly useful way to make sure you're honest about that. That is, I think. Anything else, or coffee break? Okay, great. Thanks.